So here we have a heating curve water where we have to change from 4 grams of ice at negative 20 degrees C to steam at 120 degrees C. Since they gave us water at the top, we can assume that it's water, H2O, for the ice. You can write that as one of your assumptions on the bottom. And now we have to set up that standard curve. Same thing we're doing each time. They gave you a graph just so that you have a little bit of area to write on, but we are not going to scale. Okay, not to scale. Okay, temperature is going to be on your y-axis. It's going to be in degrees C. Literally, you are going to draw diagonal, flat, diagonal, flat, diagonal, okay? And then we are going to label. The first flat is going to be our melting point. For water, we know that's 0 degrees. It's also written at the top here. If you have not put this in your notes yet, put it in your notes. We have waters and benzenes here. Okay. You could also call this hexacarbon hexahydride. Right. And then our next flat line is at 100 degrees C, and that is our boiling point for water at standard pressure, okay, of 1 atmosphere. Our first line down here is our solid line. Our next one is our liquid. Our last diagonal line is our gas. Okay. For the solid, we'd use the C of ice, 2.06 joules per gram degree C. Liquid, C equals 4.184 joules per gram degree C. And our C for a gas, 2.03 joules per gram degree C. And then our flat lines here are when we're actually going to have those phase changes. So this first one is when we are melting. And we are going to use the delta H, or the change in enthalpy of fusion, which is 6.02 kilojoules per mole. Our second flat segment is here, and that is when it is boiling. And we're going to use the delta H of vaporization, which is 40.79 kilojoules per mole. Every single time, write your enthalpies for your flat ones and write your specific heats for your diagonal ones so you don't mix up what to use where. Okay. And if you remember, if it's a diagonal line, we are going to be using our MCAT equation. Okay. And if it's a flat line, we are going to be using our change in enthalpy equation. So you have those two equations written right there. We need to walk our path. We have 4.5 grams of ice at negative 20, okay? So this is 0 degrees, again, not to scale, so you can put this dot anywhere along here that you want, okay? And then label it. Negative 20 is our temperature initial. That's the start of the whole process, okay? And then our temperature final is 120 degrees C, so that's somewhere on this last line segment, and label it temperature final. So the path we're gonna walk is finding the heat of this first diagonal segment. I'm going to call that guy A. And then our flat line segment, call that B. The next diagonal, C. Next flat, where it's boiling, D. And the last diagonal, E, when it's in its gas stage. Okay, which we know because we can look down at our notes. So anytime you can refer back to your notes. Oh, and I wrote my diagonal just a little bit longer since my dot was here. That's fine, as long as I remember that for this guy, at the end, my total Q is going to be the Q at A plus the Q of line segment B plus the Q of line segment C plus the Q of line segment D plus the Q of line segment E, where we stopped at that temperature final point of 120 degrees. And what did they want it in? In kilojoules. Kilojoules. So make sure that when you are done with your conversions, that you are writing everything in kilojoules today. All right, Q of A. A is on the diagonal, so it's MC delta T. What's my mass? 4.5 grams. What's my C? 2.06 joules per gram degree C. What's my temperature? All right, let's go to the graph. We're going from -20 to the end of line segment A, or 0 degrees. So temperature final is 0 degrees minus temperature initial. Okay, it's not 0 minus 20. Remember, -20 is its temperature initial. I'm subtracting, because delta T is T final minus T initial. It's not T final plus T initial. And so that's going to give us, our grams are canceling, our degree C is canceling. Our answer is going to be in joules. 4.5 times 2.06 times 0 minus the -20 is 0 plus 20, or 20. So 4.5 times 2.06 times 20 gives me 185.4 joules. My answer needs to be in kilojoules. So let me just convert that right now. There's 1,000 joules and 1 kilojoule. Joules goes on the bottom, so you can cancel. 0.1854 kilojoules. Sig figs, 2 sig figs, 0.19 kilojoules. So the Q for line segment A is 0.19 kilojoules. Q for line segment B. B is a flat line, so I'm going to use N delta H. I don't have a number of moles. It didn't tell me number of moles, so I'm going to use my molar mass. Little side quest here. 4.5 grams of water, where 18 grams of water is 1 mole. So that's going to tell me I have 0.25 moles of water each time that I do it. Okay. So my N for equation B, 0.25 moles times delta H. Which one do I use? The one for fusing, because solid, think solid is when you fuse things. So we're going to use 6.02 kilojoules per mole. 6.02 kilojoules per mole. Okay, and to 2 sig figs, that's 1.5 kilojoules. It's already in kilojoules, so I don't have to do anything else. QC is on the diagonal from 0 to 100. QC, 0 to 100, MC delta T. My mass is 4.5 grams. What is my C for this line segment? Oh, it's liquid water, 4.184. And what's my delta T? My final is 100. My initial is 1. 4.5 times 4.184 times 100. 1883 joules. Okay, and I need it in kilojoules. There's 1,000 joules and 1 kilojoule. Okay, and only 2 sig figs. So 1.9 kilojoules. Okay. QD. QD is the flat line, so I'm going to use N delta H, and I'm going to use the heat of vaporization here. N delta H, 0.25 times 40.799, or 40.79 kilojoules per mole. 0.25 times 40.79 gives me to 2 sig figs, 10 dot kilojoules. And QE. Diagonal line, MC delta T. Okay, and I'm going to use this C value of 2.03. M is 4.5, C 2.03, delta T. What is my delta T? Well, I'm ending up here at my absolute endpoint of 120, and I started at 100. So 120 minus 100. 4.5 times 2.03 times 20 to 2 sig figs, 180 joules, because my MCAT equation is in joules. So I need to convert it into kilojoules. 0.18 kilojoules. So QA plus QB plus QC plus QD plus QE. Okay, QD 10 dot, QC 1.9, QE 0.18. If you want to put these in parentheses if the dots are getting confusing there, go for it. QB 1.5. And QA 0.19. Okay, and my total kilojoules, 13.77 or 14 kilojoules for 2 sig figs. So you notice some part of the processes have a lot more effect than other parts of the processes, and that's okay.